So this is the first of several lessons leading to the idea of, I guess, we call curve sketching, which is using what we know about derivatives to essentially get a feeling or determine the behavior of various functions from looking at the derivatives, not by just plotting points or graphing them. It leads to the ideas of how we can therefore visualize the graph of various functions or relations, but by looking at their derivatives and various derivatives, first derivatives, second derivatives, and so on. There will be a total of 4 lessons looking at this in various ways. This is something that is probably right up there with the most challenging parts of the course. That's why I'm breaking it up over several days. And I'm just saying that just so you go into it realizing why I'm spending several days on it, and to kind of look at this kind of step by step, but never be surprised if you find things challenging. But just because we find something challenging doesn't mean we are destined to be confused at all times. But with that said, what I start with here is just some function, f of x. I have no points labeled in terms of coordinates. I don't even have the x and y axes drawn. It's just we have this function here. Okay, and I want to start with some terminology here that we're going to be using a lot. So notice this particular function has an endpoint at f, and it goes on indefinitely to the left of a. So first thing I want to label when I talk about an endpoint, for example, like f right here. This is an endpoint. And I'll label that more, but f again is what we call an endpoint. And again, if this was over here, if this was not going on indefinitely, there'd be another endpoint to this particular function. All right, a few things. If I look at, let's start with, I'll start with this endpoint actually over here. Not only is this an endpoint, this particular endpoint is the absolute max of this function. Which means this particular point, and don't assume endpoints are always the absolute max, but in this case, this particular point, notice, has the highest value of this entire function. No other point in this function is as high as this. So this is what we call the absolute maximum of this function. It's the absolute highest point of the function. And sometimes it's an endpoint, but don't assume it has to be an endpoint. All right, let's kind of work my way, maybe I'll work my way left. Let's look at e. E is first, notice in terms of a derivative, it's where the derivative equals 0. So I'll say at this point f prime, I'll just say f prime. F prime equals 0. Now this particular point, it's also it's a vertex. This particular point is what we call the local max. Sorry, local min is what I meant to say. What do you know? I said the wrong word. And by that I mean it's not the absolute lowest point of the entire function, but in its sort of region, in its local neighborhood is actually what we say. In this sort of area around here, it is the lowest point. So we call that a local max. Local min. Let's see how many times I say the wrong word. If I go over to d, in terms of a derivative, if I look at d, the derivative here does not exist. In this particular area, though, it's the highest point in its little neighborhood, in this local area. So we call this a local max. And notice at that point, the derivative is undefined. You can't find a derivative at that point because there's a corner or a cusp there. It looks more like a corner to me, but it's hard to know without more details. It doesn't really matter, though. Okay, let's look at c. Well, here again, the derivative at this point is 0, and we call this a local min. This particular local min is lower than e, but it doesn't matter. In its area, it's still the local min, we call it. And so hopefully now, as we work our way to b here, we can see that not only is the derivative at this point 0, this is another local max. Again, it's not the absolute max. The absolute max was at endpoint. That's the highest point. Literally, it's the greatest y value. And then it leads me to my last point, a. Now at a, the derivative does not exist. But this is neither a max or a minimum. And if I just look at this area, again, it's distinctly different from all the previous examples. It has the derivative is not defined, which we saw for that point in D, but at this particular point, it's not a max or a minimum. And so lastly, if I look at this whole graph, point F was the absolute max in this case. So, and there's lots of local mins, but what's the absolute minimum? Well, this particular function has no absolute minimum, and that's because it just keeps going down forever. And so we say this, we say f has no absolute minimum. And that's just because, again, it just keeps going down forever. Whatever value you may think is the lowest, there's always something lower. That's it. If I change this function for a moment and I made this an endpoint, then that would in this case be the absolute minimum, because that's the lowest. If you look at the entire graph, that's the lowest point. But I want to go back to how it was. So this kind of random function shows us many different things. OK? Now, if we just look at this function, these points here I'm going to highlight in yellow. They're points that kind of, even if I didn't actually put a dot there, they would points that would probably kind of stand out to you to the function. Even that point A, that's not a local max or min, I'm sure you would notice that little kink in the graph. All these points are what we call critical points, or critical numbers. And what they have in common is they all have derivatives that are either 0 or do not exist. And anytime a function has at some point a derivative that is equals 0 or does not exist, at that point we call that a critical point or a critical number. And by their name, they're pretty important aspects of this function. But let me label this down here. So I'll say in this case A, B, C, D, and E are all critical points or critical numbers. I'm going to make that a little bit neater. That's a phrase we're going to be kind of hearing from here on in. Now, just to kind of mention the difference between the phrase critical point and critical number. If you're looking at this as a graph and you're a two-dimensional graph that has x and y coordinates like this, like you're actually looking at it like this, we'd call these critical points because you see these points. When we use the phrase critical numbers, that's more when we're referring to just the x value. Whatever the x value was for those points, we call that the critical numbers. But they're all definitely related. OK, so let's use this now. And what we've learned before is to try to visualize a particular function with these set of characteristics. OK, I want to sketch a function that has all the following properties. So I'll read these out, but then I would highly recommend you just try as much of this as you can on your own without watching me do it right away. But I want a function that has a domain from -5 to 5, including -5, not including 5. Has exactly 2 critical numbers somewhere in the domain. It has a critical point when x equals -2. That is not an extreme value. It has a critical point when x equals 4. That is an absolute maximum. I want the left endpoint to be the to be the local minimum, and I want no absolute minimum. All right. With that said, there are countless ways of doing this correctly. There are countless ways of doing this incorrectly, but all the correct functions have a few things in common. And so, highly recommend you don't just watch me do this. Pause the video, and I'll work through it in just a moment. Maybe I'll have a sip of coffee. Wake me up. Oh, that was tasty. All right, hope you've tried this already. So first, I don't really have to, but let me set up a little quick sketch for x and y axes here. OK, so first, the domains from -5 to 5. I'm just going to put those on my axes. So -5 to 5. OK, I also got to remember, though, if I look at the domain, -5 is included, 5 is not. There's 2 critical numbers in the domain. Well, then I tell you what they are. They're at -2 and 4. So let me kind of just label -2 right here and 4 right here. So those are going to be some of my critical numbers. When x is -2, it's not an extreme value. It's a critical point, but it's not an extreme value when x is -2. So let me highlight that point there. So that means if I look back to my example up here, that's similar to what I had for A. A is a critical point, but it's not a maximum or a minimum. So some sort of kink or something like that. But again, it's, I shouldn't even say that. I shouldn't even say it's a kink. There's a lot of different possibilities. But it's, again, it's a critical point, but it's not a max or min of any type. That's it at 4. That's an absolute maximum. So that's a little easier for me to start drawing. So I'm just going to pick a point when x is 4. It doesn't even have to be above the x-axis, but I'm going to draw it above the x-axis. I don't know how about here. And I now know that's the absolute maximum of this function, which means I know around it, it must look something like this. However, when I say something like this, it also, honestly, it could be something like this. It could be something like this. There's lots of possibilities, as long as that's the highest point. As long as it goes up and then back down, I'll leave it like that. Now, there is no absolute minimum. So how on earth can that be? Well, notice my domain is from -5 to 5, but not including 5. And if there's no absolute minimum, that means this function, if I look at, compared to my example below, one way of doing that is if it just keeps going down forever. There's other ways to have no absolute minimum, but one way is that it just keeps going down forever. And so if it keeps going down forever, but it has a domain from -5 up to 5, not including 5, well, then what I can do is I can make 5 a vertical asymptote and have this function just keep going down like that. So notice, this function is going down forever. In fact, I'll make my marker a little darker. But because there's a vertical asymptote there, the domain will never reach 5. It never reaches a minimum because it just keeps going down forever. So I have no absolute minimum. And I have an absolute maximum when x is 4. So all that's really left for me to take into account now is that the other side of the domain, at -5, there's going to be an endpoint there somewhere. But at -2, there has to be a critical point, which means the derivative is, there's some sort of critical point that is not an extreme value. It's not a maximum or minimum of any type. So for example, I just draw a dot here. I can't be like that, because then that would be an extreme value. That would be a local minimum. I know it can't be like that, because that would be an absolute maximum. It can't be just like this, because that would not be a critical point. Again, if we look back up here, these critical points I've all highlighted, what they had in common is they all had a derivative of 0 or a derivative that did not exist. So I can't be that either. So I have to find a way to make it so the derivative is either 0 or does not exist without it being a max or a min. And so I'll say one thing I could do is I could have something like I drew in the previous example, something like this and then like this. And that would work. And that's totally great. Or I can show something like this, where it's almost like a cubic function. It has a multiplicity of 3, kind of, where it goes like this and then back up. So I'll leave it like this just because I want to show us a variety of examples. If I just kind of connect this, and then, I don't know, somewhere here, 5, have it end. So I said there's an endpoint. And so now that I've sketched this out, let's just look at all the characteristics. Is the domain from -5 up to 5? Yes. It includes -5, does not include, includes -5, does not include +5. It has 2 critical numbers. Yeah, at -2 and 4, and no other. There's no other critical points here. For example, if I drew something like this, if I had this going down then back up, then there'd be another critical point down here. But it says there's exactly 2 critical numbers. When x is -2, it's not an extreme value. It's a critical point. The derivative is 0 there, but it's not a max or a min. +4, it is the absolute maximum. Yep. And the left endpoint, oh, I forgot about this point here, but it's a good thing it's correct. The left endpoint is a local minimum, and that is correct. That's it. Now you may say, isn't that the absolute minimum? No, because there is no absolute minimum. Remember, this graph goes down forever over here. So this is a local minimum. And so it fits all the characteristics given. All right, so next. I don't want us to get too thrown off by all the writing here. Essentially, a lot of this repeats what I've already mentioned, just kind of formalizes it in words. But this extreme value theorem pretty much just, you can read it yourself, but essentially means if you have a function in a closed interval, which means it has endpoints, okay, and it's continuous. So, there's no asymptotes or discontinuities in between. If you have some continuous function that has a beginning and an endpoint, that's what a closed interval means. A and B are both included. So the last example, this was not a closed interval because it didn't include 5. But if you have a function on some sort of closed interval where A and B are endpoints, then there has to be a maximum and a minimum somewhere in that interval, which just makes sense. If I'm going to draw something that has a beginning and an end that is also continuous, I don't know. There we go. Somewhere in this curve, there must be a highest point. It looks like it's there. And somewhere there must be a lowest point. It looks like it's barely there. Doesn't matter how I draw it. OK? Even if I draw something. Oh, what did I just do? I think I'm OK. Even if I draw something that's just a horizontal line. OK, that's a closed interval. It's continuous. It has a maximum and a minimum. They're the exact same. OK? But so that is still, the whole thing is both a max and a min. But it's also kind of boring, just a horizontal line. But again, if I just draw anything, oh, sorry, I don't know what's going on with my device right now. There we go. OK, as long as there's endpoints, there is a absolute minimum, there's an absolute maximum. So that's essentially what the extreme value theorem says. It's kind of it just makes sense once I just kind of draw a few examples. However, as it says, if f is not continuous, or if f has an open interval where it doesn't have endpoints, at least of one of them, then there may not be a maximum or a minimum. And we saw that in the last example. There was no minimum. It went down forever. It had an absolute maximum, but it had no minimum value. Like I mentioned before, if a function has a local max or a min, then it exists at a critical number, where either the derivative is 0 or the derivative does not exist. And I should actually say here, or at an endpoint. Again, a max or a min value, it could exist at an endpoint or at a critical number, but it's going to have to be one of those. And so how do you find these absolute maximum and minimum values on some closed interval? Well, and I'll do this in a moment, find the critical numbers, find the values of those critical numbers, and values of the endpoints. And then from there, you should be able to tell what the max and the absolute max or min is. And again, if it's a closed interval, there will always be a maximum somewhere and a minimum. As always, the best way of understanding this is to try it. I think I have just one example here to try. With a relatively simple function. OK, so here's the graph of negative x cubed plus 2x minus 2 in the interval negative 2 to 1. So that's what I have graphed right here. And so I'm just going to label this just so we're really clear. That is at negative 2. This is at 1. So what am I asking? Determine the x-coordinates of all the extrema. The x-coordinates of all the, that's a fancy word for the location and values of absolute and local maximum minimums. Extrema just means the extreme values, essentially. So I can just tell by looking at this. Now, don't assume I'm always going to give you a graph, but I can tell right here at negative 2, that's the absolute max. When x equals 2. Now, obviously, a good question would be, what if I didn't give you the graph? Well, I want to show you. But I can just see right now that's the absolute max. I can see down here. Now, wherever this is, I don't know yet where that is. But I know that's my absolute min. Again, I can just see it from looking at the graph. I can also see by looking at the graph, there is, if I look over here, there's another critical point right here. That is a local max. But again, the x value, the critical number, I don't yet know. And then I have another local min at the very end. I know that's when x equals 1. That was told to us by looking at the domain. I'll put up here x equals 2. OK, so right now, because I have a graph, my main task is to figure out what is the x value of this absolute min. What's the x value of this local max? OK, I can see roughly where they are, but how can I figure that out? And in the end, more important, how could I figure out all this if I didn't actually give you the graph, but just gave you the equation and the domain? Well, first, let's find my derivative. And the good thing is this is a pretty simple function to differentiate. So dy dx, just in the power rule, is negative 3x squared plus 2. So my derivative is a quadratic function. And so now let's remember some of the things we saw. I have to find the critical numbers. And the critical numbers, or the critical points, are where my derivative does not exist, or where my derivative equals 0. So let's look at these for this particular derivative. Where will my derivative not exist? Well, nowhere. This derivative always exists. There's no reason that negative 3x squared plus 2 would have any non-permissible values. It exists everywhere. And so I'll make that comment first. And so I'll say dy over dx always exists. And maybe I'll say in the domain. And I just said in the domain because in this case it doesn't really matter. It's a cubic function which becomes a quadratic function when you differentiate it. A quadratic function has a domain of all real numbers anyways. But let's say the function was different. So there may be places, for example, that dy dx, depending on the function, you could not differentiate it, or so you can find the derivative. But you have to make sure that's still within the domain. For this particular function, it doesn't really matter. That's it. What will happen is where dy dx equals 0. And so for that, I just need to take my derivative and make it equal 0. So I get 0 equals negative 3x squared plus 2. So let's figure out where my derivative equals 0. That's where 3x squared equals 2. That's where x equals plus or minus root 2 over 3. So these are my critical numbers. There are 2 critical numbers. Now, keep in mind, I can do that from looking at the graph. But if I didn't have the graph, I now know there are 2 critical numbers, or 2 critical points. Which means in this case, I now know the coordinates of these 2 critical points that I didn't know about before. This absolute max, I now know must be the minus root 2/3. And this local max over here must be positive root 2/3. There we go. OK, so in terms of the questions asking, I think I've answered everything. Determine the x coordinates of all extrema. And so I've done that. All the extrema have been labeled. So keep in mind, if I didn't have the graph, I would have now, without having the graph, I would now know these 2 critical points. The only thing I wouldn't know from looking at the graph right away, the only thing I wouldn't know if I didn't have a graph immediately is these 2 endpoints, except once I look at the domain, I know there's endpoints there. And if I notice the question is just asking for the x coordinates. So while I labeled this absolute max and absolute min, it didn't actually ask for that. It just asked for where are, the x values, where are all the extrema. And so I know there have to be something happening at the endpoints. And I now know my critical numbers here. And lastly, let's say I wanted to know the y values of these points, right? Notice none of these points will actually give you the y values. I can see roughly where they are in terms of comparison to one another, but I don't actually know the y values of any of these points. That said, it'd be really, really easy to find them. So, sometimes a bit tedious, but not difficult. The way I can find the y values of any of these points is just taking those x values I know and putting them into my original function. Right? If I want to know any of those y values, just replace x with what I have right here, and then I'll have my y values. Again, sometimes it's annoying to calculate all these things, but it's not difficult. You're just substituting into the original function. All right, so before I finish this, keep in mind some of the pivotal parts here is not so much memorizing what the extreme value theorem is, but knowing what a critical number is and just having a feeling for how you find a critical number and what it represents. Again, a critical number is where the derivative is 0, does not exist. Having a sense of what these phrases absolute max, absolute min, and local max and local min all mean. Understanding how if a function is not on a closed interval, like this example here, if, for example, in this case, it never reaches 5, how it doesn't have to actually have an absolute max or an absolute min. But if something does have a closed interval like this, there has to be an absolute max and an absolute min. There has to be. There may be a tie for them. There may be more than one, but you can't say there's no absolute max or absolute min if a function has a closed interval and it's continuous like this. We're going to do a lot more with this over the coming days, but this is a good place to stop right here.